This is chapter 2 of Chemistry 1411. In this chapter, we're going to be talking about atoms, molecules, ions, and there's a little bit of nomenclature. So make sure you stick around for the nomenclature part, and we'll go through that information. So let's start with Dalton's atomic theory. This is a good place to start because in the early part of the 19th century, the English physicist and chemist John Dalton, this guy right here, who's here looking very British and also looking very pensive, he had what we call Dalton's atomic theory. Now, he did other things, as we will see as we move on through the semester, but this is one of his most famous things. And really what he was doing was collecting a lot of the information that was available at the time, telling us about how elements worked. And so he held 4 postulates in this theory, and he held that these things were true. And the very first thing is that each element is composed of extremely small particles called atoms. Now, his view of the atom was a little bit different than our view of the atom. He thought that atoms were indivisible particles, that there was nothing smaller than the atom. And while that is almost true, it's not quite true. We know that there are protons, neutrons, and electrons, but we haven't gotten there yet, so we'll talk about those in just a bit. But we want to look at we'll go with this. This was the main accepted theory at the time once he published this. Next, all atoms of a given element are identical, meaning all carbon atoms are exactly the same, all oxygen atoms are exactly the same, and so on and so forth. All right, but the atoms of one element are different from the atoms of all other elements, meaning that all carbon atoms are different than all oxygen atoms. All right, we will find that that's not quite true. We know now that all carbon atoms are definitely different than all oxygen atoms, but we will find that it is possible to have different isotopes of the same element, meaning that they have different numbers of neutrons. But again, he didn't know about neutrons, so we can't blame him for that. Atoms of one element cannot be changed into atoms of another element. So when you're doing a chemical reaction, you cannot change carbon into oxygen. It just doesn't work. All right, so you cannot do that. Furthermore, atoms can neither be created nor destroyed in chemical reaction. So when you're doing some sort of chemical reaction, we cannot lose atoms or gain atoms out of nowhere. All right. 4, compounds are formed when atoms of more than one element combine, and then a given compound has the same relative number and kind of atoms. What this means is, for example, if you want to form water, water has hydrogen and oxygen. It's called H2O, or has the symbol H2O. And since it has the same relative number, there's always 2 hydrogens for every 1 oxygen. And that's an example of that. All right, so the implications of this are pretty big, and we want to cover a couple of those and make sure that you get what is going on here. So first of all, Dalton's atomic theory, it does explain the law of constant composition. We saw this back in the previous chapter, which is that if you've got a sample of water, that water is always going to have 8 grams of oxygen for every 1 gram of hydrogen, and it's always in that ratio. All right. And so if they always have the same ratio of atoms, then of course they're going to have the same mass ratio as well. So it explains the law of constant composition. It also explains the law of conservation of mass. If atoms can neither be created nor destroyed, then that means that the mass cannot be created or destroyed. So we want to look at number 2.10 on the in-class assignment. Let's scoop down here. All right, and a couple of you have asked about this, and by the way, you do not turn in these in-class assignments. You keep these so you can study with them. All right, so here we go. All right, chapter 2, and we got our in-class assignment here. Okay, so hydrogen sulfide is composed of 2 elements, hydrogen and sulfur. In an experiment, 6.500 grams of hydrogen sulfide is fully decomposed into its elements, if 0.384 grams of hydrogen is obtained, how many grams of sulfur? All right, well, this is just a simple subtraction problem. So we'll do 6.500 grams, and we'll subtract 0.384 grams, and then I'll go ahead and write this out: hydrogen sulfide, and then here, this is the hydrogen. All right, so we want to figure out how much sulfur there is going to be, and the amount of sulfur is simply going to be the difference. All right, the difference between those. So we will take the difference, so 6.500, and we will subtract 0.384 grams, and we get 6.116 grams of sulfur. All right, so since the hydrogen sulfide is only made up of two things, part of it's hydrogen, the other part is sulfur, and then that's it. That's all that we have. Now, on what fundamental law does this experiment demonstrate? So what fundamental law does this demonstrate? And this demonstrates, so part B here, this demonstrates the law of conservation of mass. Right, because the total amount of mass is constant. And then part C, how is this law explained by Dalton's atomic theory? Well, if we go back and look at postulate 4 of Dalton's atomic theory, which I'm going to go back real quickly and show this to you. Let's see, Dalton's atomic theory. Oh, actually, postulate 3, sorry about that. Let's see, postulate 3 says atoms are neither created or destroyed. And since the atoms are not created or destroyed, it's the law of conservation of mass must be true. So I'm going to come back over here, and we will write postulate 3. And that, again, is just a statement of the law of conservation of mass. All right. All right, so now what we want to do is we want to look at the law of multiple proportions. And this says that we can have more than one compound with any two, with a particular set of elements. For example, there are two compounds that contain hydrogen and oxygen, or at least two simple compounds. One is water, H2O, and the other one is hydrogen peroxide, H2O2. And so we will find that if we take the ratio of those masses, so the ratio of the ratios of those masses, rather, that we're going to get small whole numbers. Now, the ratio of the ratios seems a little bit strange, and so the best way to demonstrate this is using the example number 11. But here we see if two elements A and B combine to form more than one compound, the masses of B that can be combined with the given mass of A are in the ratio of small whole numbers. So in other words, the ratio of B to A, if we take those ratios for the different compounds, those ratios are going to be in the ratio of small whole numbers. Again, the best way to do this, to show you this, is just to do one of the calculations. So we're going to do the calculation here. So a chemist finds that 30.82 grams of nitrogen will react with 17.60 grams, 35.20 grams, 70.40 grams, and 88.00 grams of oxygen to form 4 different compounds. We want to calculate the mass of oxygen per gram of nitrogen in each compound. So simply, we are going to take each of those numbers of oxygen, so 17.60 grams, and divide by the mass of the nitrogen, so 30.82 grams. And that's going to give us a number. And let me clear that out. And you'll see the number that we get there is 0.57, and we have 4 sig figs, so I'm going to do 5711. All right. So let's do the other ones. So 35.20 grams divided by 30.82 grams. And we get 1.142. All right, so we'll do these other calculations real quick. I'm going to turn off my microphone for just a second. All right, so now that we've done those, we've calculated the mass of oxygen per gram of nitrogen in each compound. We want to see how these numbers support Dalton's atomic theory. And the way that they support Dalton's atomic theory is that we will see that these numbers are in the ratio of small whole numbers. In other words, if we take each of those numbers and divide by the first one, each of those ratios and divide by the first one, we're going to get a whole number. So for example, if we do 1.142, obviously if we take this one and divide by itself, we get 1. But if we do 1.142 and divide that by 0.5711, all right, so the ratio of the ratios, so 1.142 divided by 0.5711, you'll see we get 1.9996, which that's close enough to 2 that we can round that. Similarly, if we do the next one, so 2.284 divided by 0.5711, so 2.284, we get 3.999, which that is close enough that we can call that 4. And then finally, with the last one, 2.855 divided by 0.5711. And we get 4.999, which I think everybody would agree that that is close enough to 5 that we could round that. So again, and when we go back and look at the law of multiple proportions, all right, and so I'm going to say this supports the law of multiple proportions. Okay. If we go back and look at that law of multiple proportions, which we saw back over here, that if two elements A and B combine to form more than one compound, the mass of B that can combine with the given mass of A are in the ratio of small whole numbers. So these are the mass of oxygen that can combine with a given mass of nitrogen. So we have those numbers, and that those numbers are in the ratio of small whole numbers. And so these end up being different compounds. Now, in case you're curious, I'm going to show you what those compounds are. At this point, we wouldn't be ready to come up with these compounds on your own, but I can show this to you in the next chapter. After the next chapter, you would be able to do this. But if you come, you'll see this one is nitrogen dioxide. This one is simply going to be NO, so nitric oxide. This one was dinitrogen monoxide or nitrous oxide. This one's nitric oxide. This one is NO2, and that is that brown gas that I showed you in the previous chapter when you took the penny and put it in nitric acid and a brown gas came off. That's that nitrogen dioxide. Nasty stuff, by the way. And then this one is N2O5. N2O5. Now, one thing I like to point out about these is that these compounds each have different properties. The first one, N2O, nitrous oxide, it's laughing gas. And so if you were to breathe in this, it would make you kind of giddy and kind of oblivious to everything. NO, this one's nitric oxide. If you breathe that one in, it makes you dead. Well, if you breathe it in any significant concentration. NO2, in a very similar fashion, nitrogen dioxide. This one is very unpleasant to breathe in any significant concentration. So if you were to breathe that one in, you would have a great deal of discomfort and possibly die. And then finally, N2O5, if you were to breathe this in, it would come in contact with the water in your lungs and it would convert into nitric acid. And so you would be equally dead. So just to sum this up, laughing, dead, dead, dead. So if you have to pick one, the N2O is the better one. But, maybe just stick with oxygen for now. That's probably your best bet. All right. Now, back to our presentation. We want to talk about the other aspects of the atom, and for this, we want to look at what's called the cathode ray tube experiment, which was done by J.J. Thomson. So this is a cathode ray tube. The way that a cathode ray tube is set up, there is a cathode, which is this. That's the negative electrode on a strong electric source, so a DC power source. And then here we have A, which is the anode, and it is the positively charged electrode. And then it has a little hole in it. And then here, this is a slit. And the reason that we have the slit is that we're going to have particles that flow from our cathode to our anode. And then over here, S is our screen, and that is a phosphorescent screen. When the charged particles that come out of the cathode hit the screen, they will glow. And that way you can tell where those particles have gone. So particles will be emitted from the cathode through the anode, through a slit, and then hit the phosphorescent screen. And so that's sort of the basic setup for our basic setup for Dalton's cathode ray tube experiment. So particles are emitted from the cathode through the anode to the phosphorescent screen. Now, all kinds of interesting things occurred when scientists they made these and they started playing around with them. They found if they got a magnet that they could cause that beam to be bent. And so if you take physics, you'll find that there is a direct connection between magnetic fields and electrical fields. I'm gonna save that for your future discovery. But you'll notice here I've got two plates, and so J.J. Thomson had set this experiment up towards the end of the 19th century. He had set this experiment up so that he had a positive and a negative electrode that were on either side of the beam. And so when he turned the beam on, it went straight for the screen. When he turned on this electric field, he found that the particles that were emitted out of this cathode were deflected away from the negatively charged plate. And so he determined that these things must be negatively charged. And of course, if it's a negatively charged particle inside the atom, we all know exactly what that must be. That must be the corpuscle. All right. Well, that's what J.J. Thomson called them. Other people never really stuck to the name called corpuscles. Instead, a name that had been proposed by G. Stoney was the electron, and that is what, of course, stuck. That's what you guys all know as the electron. But here's the big deal. J.J. Thomson discovered the electron. If you're going to say, hey, what's the one thing I need to know about J.J. Thomson? He discovered the electron. All right. Now, he discovered a lot of other stuff. All right. I don't want to sell him short, but he discovered the electron, and that's the main thing I want you to know about J.J. Thomson, and of course, have a basic understanding of the cathode ray tube experiment. Now, doing some math, he was able to determine what the charge to mass ratio was on those electrons. So if you took the charge of the electron and divided by the mass of the electron, you would get this number. Now, he didn't know what the charge on a single electron was, and he didn't know what the mass was, but by doing the math, he could at least get this ratio. And with that ratio, you'll see 1.76 times 10 to the 8th coulombs per gram. Now, interesting little side story here. The unit coulomb, which is it's the unit for charge, it's our SI unit for charge. That unit was sort of invented and / discovered in the early part of the 19th century. Many decades before J.J. Thomson was even doing anything, much less a cathode ray tube experiment. So when Thomson did this experiment, he used the units for electricity that were already in place. And the reason for this is electricity was very well studied in the 19th century. Maxwell's equations, if you're not familiar with Maxwell's equations, you're in for a treat when you study that. But Maxwell's equations very extensively looked at the math behind electricity and magnetism, for that matter. It's absolutely beautiful. So when you take physics and you get to Maxwell's equations, just enjoy how beautiful those equations are. All right. Here's the interesting part. Electricity was very, very well studied before they realized that electricity was electrons flowing, which that's kind of amazing. So now, another thing that was interesting about this experiment, you remember the picture I showed you on the previous page? Well, on that picture, on the previous page, the cathode could be made out of different metals. It could be made out of iron or gold or copper or silver or platinum. And in fact, you can even make it out of something that's not a metal. Well, what Thomson discovered was regardless of which metal he used, he always got these same particles, and they always had the same charge to mass ratio. Therefore, he determined that these electrons must be a constituent of all matter. And that was a big deal because John Dalton at the beginning of the 19th century had told us that atoms were these indivisible particles, that there weren't smaller bits than the atoms. And that's just simply because Dalton didn't have all of that information. So this is inconsistent with Dalton's atomic theory that atoms must be made of something more than just, single spheres. They have to have other stuff in them. So Thomson, there was a need for a new model of the atom. We couldn't just have spheres. And so he came up with something that we call the plum pudding model. And the plum pudding model says that these electrons are the small particles that float around in a sea of positive charge, kind of like plums in pudding. All right. And so there is our plum pudding model. And there, of course, is Homer Simpson wanting to eat the plum pudding model. So that was the sort of working model of the atom. But of course, if you know anything about the structure of the atom, this is not what atomic structure looks like. So we need to go a little bit further. Now, before we dig into talking about the true structure of the atom, we do need to take a little sidestep here, and because I'm going to go back here, you'll see that Thomson was only able to come up with the charge to mass ratio. He didn't know the mass and he didn't know the charge. And so in order to do that, there was another scientist who we're going to look at, and that other scientist is Robert Millikan. And Robert Millikan did an experiment that's called the oil drop experiment. And instead of me explaining what this is, I'm going to use this video that is here. And so just bear with me for a second as I pull up this video, and we are going to start the oil drop experiment video.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, The fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
All right, so that is Robert Millikan's model. The key thing here is that by doing this experiment, Robert Millikan was able to determine the charge on a single electron. Again, each oil droplet had at least one electron that was attached to it, and then by doing some very, very complicated calculations, he was able to come up with the charge on an electron of 1.6 times 10 to the negative 19 coulombs. Well, using that and the number that we got previously from J.J. Thomson, which was the charge to mass ratio, if you have this and the charge to mass ratio, you can get the mass of a single electron, which Millikan also did. He got the mass on a single electron. I'm not going to go into the details of this experiment other than what I showed you on the video, but I will say that this is not a trivial experiment to do. You kind of need to know what you are doing. And kind of some interesting problems that he ran into. One is that when he first started doing this, he did it with water, and he found that the water droplets would start to evaporate as they fell down this little chamber. And so the water droplets weren't going to work. So he had to switch to something that was not volatile, that didn't evaporate. So, all right, that's all kind of interesting. But again, Millikan, he gave us the charge on an electron, and from that also gave us the mass of an electron. All right. Well, towards the end of the 19th century and the beginning of the 20th century, scientists had discovered radioactivity. And there were three main types of radioactivity that they had discovered at the time. And those three types were alpha, beta, and gamma radiation. And so different kinds of radioactive materials will give off these different types of radiation. And so Ernest Rutherford became very interested in alpha particles. Now, he was interested in the other stuff as well, but he got some of these samples of radioactive materials, and he really wanted to study these alpha particles. The information that was known about the alpha particles is, one, that they have a positive 2 charge, and that they are much heavier than the electron. All right. There's also beta particles, and beta particles are essentially just electrons that are ejected out of the nucleus. And if you're wondering how that's possible, you'll just have to wait around till General Chemistry 2 when we talk about that. So beta particles have a negative 1 charge, and they are much lighter than the alpha particles. And then also gamma radiation. Gamma radiation is a massless radiation. It has no charge and no mass. It is electromagnetic radiation, so it is different. And it is possible to have more than one of these happen at the same time with a given particle, but Rutherford was very interested in studying these alpha particles. So again, alpha particles, they're heavy compared to electrons, and they have a positive 2 charge. So he said, let's take some of these alpha particles and we'll shoot stuff with it, pretty much. All right, so here is the experiment where he shot stuff. All right, so he took some of these alpha particles and put them into a container, and he aimed them at a very thin piece of gold foil. And by very thin, I mean extremely thin, very, very thin, just a few layers of atoms thick. All right. So he aimed that beam of alpha particles at the gold foil, and he expected them to fly through. In fact, he said in his paper he expected them to fly through like cannonballs through tissue paper. I'm paraphrasing there, but cannonballs through tissue paper. And so he found that most of them flew right through, like cannonballs through tissue paper. However, so most of them just flew right through. However, some of them were deflected at slight angles. And some of them were even deflected at greater angles. And in fact, some of them hit the gold foil and bounced right off. So you can imagine the result where if you aimed a cannonball at a piece of tissue paper, you shot that tissue paper, and the cannonball bounced back. That would be a surprising result and a very much unexpected result. So using this and looking at the math of how many pass through, Rutherford was able to determine that all of the positive charge and most of the mass of an atom must be locked up in the middle of the atom. And he called that the nucleus. So pretty much most of the mass and all of the positive charge are in the center of the atom, and we call that the nucleus. And that the electrons must just be floating around somehow. Now, as far as how they're floating around, we'll get to that at a later point. But the main point is that Rutherford discovered the nucleus. So thank you, Rutherford. All right, and so now we've got a timeline to our nuclear atom, and I just want to go over this. All right, so back at the beginning of the 19th century, 1803, John Dalton came up with our indivisible atoms with his atomic theory. All right, thank you, John Dalton. All right, next we have the plum pudding model. With the plum pudding model, Thomson, after he discovered the electrons, he said, these electrons must be floating around in a sea of positive charge like plums and pudding. And then here we got Homer excited about the pudding. And then Rutherford said, all right, all the positive charge and most of the mass must be in the middle of the atom, and we're going to call that the nucleus. And so that gave us Rutherford's nuclear atom. And so there we go. We've got Rutherford's nuclear atom. Now, if you look closely at this picture, it does not look like the model of the atom that you were probably taught in grade school and high school. And that's because there are a few things that we haven't gotten to yet. We will get to those things. So worry not. We will get to those things, but we're not going to see the part about orbitals. We're not going to see that until chapter 6. So in case, if you really, really want to read ahead, you can jump ahead to chapter 6 and read about it. But for now, we're just going to say we've got this nucleus, and we're also going to say a few other things. There was another scientist named Chadwick who came along and discovered that inside the nucleus, there were things called neutrons. So one thing I want you to know is with our modern view of the atom, these are the things I want to mention. And that is that there are 3 subatomic particles that we are interested in here. And I want you to know the charge, location, and relative mass of these subatomic particles. And so the charge, so of course, protons are positive, electrons are negative, and neutrons are neutral. All right. And they're right there in the name. So you probably knew that. All right, let's see. Location, the protons and the neutrons are in the nucleus, and that the electrons are in a cloud outside the nucleus, and that the protons and neutrons are about the same size, but you'll notice they're not exactly the same size. All right, we'll talk about that in chapter 21. Oh my God, that's a long way away. And then the electrons here, the electrons are much, much lighter. They're about 1/2000th the mass of either a proton or a neutron. So electrons hardly make up any of the mass of a particular atom. All right. So there we go. Again, I want you to know those things. You do not need to know this is exactly 1.0073 and 1.0087. All right, you don't have to know that. And the reason you don't have to know that is, one, if you look on the back of your periodic table or your conversion chart here, let me go back over here. All right, so this is one of the pages that you can print out when you take an exam. If you're taking it at home, if you're taking it at the testing center, you will get a periodic table that has this on it. But if we look here, we've got the electron mass, neutron mass, and proton mass, and it's given there. And like I said, you don't have to memorize those numbers. You just need to know that a proton and a neutron are about the same size, and that an electron is much, much smaller. All right. All right. So next, we want to look at atomic numbers and mass numbers. So atomic numbers and mass numbers. So this is the format that we use for writing down a particular isotope of an element. And it turns out one of the things Dalton was not quite correct about is that not all atoms of the same element are identical. Not all carbon atoms, for example, are identical. So let's look and see what is identical and what's different. First of all, when we have this format, the letter, of course, is the chemical symbol, and you're quite familiar with that on your periodic table, all right, which I'm going to show you real quick, that periodic table. So here's the periodic table. We've got all of the symbols here. All right, so that's something you're quite familiar with. All right, so that is our chemical symbol. The number that's on the bottom, and again, this is just for a particular isotope. It does not tell us actually the number on the bottom is the atomic number, and all atoms of the same element have the same atomic number, and it is the number of protons that are in the nucleus. All right, I'm going to go back over here. You'll see that that the atomic number is given for each element. There's carbon, it has an atomic number of 6. Here's phosphorus, it has an atomic number 15. Here's manganese here. Manganese has an atomic number of 25. All right, so all atoms of the same element have the same atomic number. They have the same number of protons. And so really the number on the bottom here is redundant with the symbol. So sometimes you'll see isotopes written without the atomic number, because if you know the element, then you know the atomic number, as long as you have the periodic table with you. All right, the number on the top is called the mass number. Now that is a little bit of it's an approximate mass. It is not exact mass, and I'll explain how that works here in a bit. But the number on the top is the mass number, and the mass number is the total number of protons and neutrons in the nucleus. Well, atoms of the same element can have more than one possible mass number, and since they have to have the same number of protons, that means they can have different numbers of neutrons. And if you want to get, since this is the total number of protons and neutrons, and the number on the bottom is the total number of protons, then the difference between those will give you the total number of neutrons in that isotope. All right. So isotopes, atoms with identical atomic numbers but different mass numbers. And here are a few examples here. Carbon 12, if we do 12 minus 6, that of course gives us 6 neutrons in carbon 12. Carbon 13, this is another naturally occurring isotope of carbon. Turns out about 99% of all carbon is carbon 12, and about 1% of all carbon is carbon 13. And carbon 13, of course, 13 minus 6 gives us 7 neutrons. There is a tiny, tiny fraction that's like a fraction of a percent, which is why it's like 99 plus 1. What else is there? Well, there's a tiny fraction of a percent that wouldn't show up if you are measuring it just to the nearest percent. But there's a tiny fraction of carbon 14, which is a radioactive isotope. It is naturally occurring. And if you have carbon in you, which I can tell that you do because you're human, if you have carbon in you, then that means you have some carbon 14 in you. So you are radioactive. All right. Don't worry about it. That's how they do stuff like carbon dating. So 14 minus 6, of course, gives us 8 neutrons. All right, let's look at a couple of more of those, and then we're going to do a problem on the in-class assignment. All right, so how many neutrons? How many neutrons are in each of these? All right, so here on each of these, we've got potassium, K is potassium, atomic number of 19, mass number of 41. So 41 minus 19, of course, gives us 22. And if you have any doubt, just get your calculator out. But really? Okay, so 22. And then here for vanadium 50, if we do 50 minus 23, that gives us 27 neutrons. And then finally here, we've got sulfur 36. 36 minus 16 gives us 20 neutrons. Now, there are other isotopes of these elements, and these may not even be the most abundant isotopes of these elements. And we're going to talk about that a little bit later. So I don't want you to think that you can go and look at the periodic table and know what the number on top is going to be. And that's because there's more than one isotope for many of the elements. So let's look at number 23 on the in-class assignment. So the way that this works is we want to determine each of these numbers. So the number of protons, neutrons, electrons, and the mass number for each of these. And here we've got chromium 52. And since the atomic number is redundant with the element, then you'll notice that the atomic number is not written here for chromium 52. But the mass number is written, so I'm going to write 52 for that. I'm going to write 52 for that. In fact, here, I'm going to write that. I'm going to write the rest in red. I like the color red. All right, so now to determine the number of protons, this is where having a periodic table is really, really handy. So here is chromium. Chromium is element 24. That means it has 24. It has 24 protons in it. So 24 protons. And then the number of neutrons is simply going to be the mass number minus the number of protons. And again, if you have any doubt at all, just go and 52 minus 24. All right, we get 28. If we have a neutral element, that neutral element is going to have the same number of protons and electrons, so that's also going to be 24. And if you look here, these are all neutral atoms. So these are all neutral atoms. A little bit later on the next page, when we talk about cations and anions, we'll have different numbers of protons and neutrons, but we'll save that for just a little bit later. All right, next, element 25. So element 25, so we're going to go and get our periodic table here. Element 25, that is manganese, Mn. So manganese is element 25. And our mass number is the sum of the number of protons and neutrons. So 25 plus 30, I don't need a calculator for that. That's manganese 55. And then the number of electrons is going to be the same as the number of protons, so we will put 25 there. All right, next, since the number of protons and electrons is going to be the same, this is also going to be 48. And then with that, we can determine which element that is. Element 48 is right here. That is cadmium, so Cd. And then the sum of the protons and the neutrons is going to give us the mass number. So 48 plus 64 gives us 112. And then finally, we'll put 112 there for cadmium. All right, next, mass number. So we don't know what it is, but we do know it's 222. And since the number of electrons is 86, we're going to write 86 right there. And element 86, we'll go back to our periodic table here. Here's element 86, Rn, which is radon, which, by the way, is a radioactive gas. So Rn is radon. And then we'll do 222 minus 86. So 222 minus 86, and that will give us 136. All right. And then finally, we've got 207. So 207 is our mass number. It's element 82. We'll come back over here. Element 82 is Pb. That's lead. All right, the number of neutrons is going to be 207 minus 82. So 207 minus 82. And of course, that gives us 125. And since it's neutral, then the number of electrons will also equal 82. All right, and I'm going to switch back over here, and it looks like, yes, we are going to stop the video here. We're at over 40 minutes. We're going to stop the video here, and the next video will start with section 2.4.